if you look at these two figures, the figure on the left is data from the figure on the right, believe it or not. And so all we've done is we've zoomed in to get a much better understanding of how noisy what appears to be a really quiet phase is, and then how we can use that information to figure out what our start threshold should be. So all we've done is we've averaged these ground reaction force over the first 1 second. That gives us their body weight for that particular jump, and we do this on a jump by jump basis rather than relying on a scale mass. And then we're looking for the largest force within that quiet standing period. We want to know whether it's greater than the body weight, i.e. the average of 1 second force, plus 5 standard deviations, also calculated from this 1 second of standing still. If it is, then we're looking for a force threshold that's going to be greater than 5 standard deviations. If it's not, then we're looking for a threshold that's going to be less than 5 standard deviations of that mean force. And so if we look here for this example, you can see on the left that the mean force was 781.96 newtons, and so our maximum force was less than the mean force plus 5 standard deviations from that quiet phase. So actually, the starting threshold was 774.43 newtons. So we can locate that, and then as Ben suggested just now, we then sort of backward search to that last instance of body weight occurring. And that's essentially, so what we're going to have then is where the threshold breaks 5 standard deviations, whether it's plus or minus, that's where that movement actually starts. So that's the definition of when a movement begins. However, we backtrack to where the last instance of body weight is, so we can actually work on the assumption that our athlete is still standing still. And that's absolutely critical to get, or to be able to integrate our force time data effectively and accurately.